Hello everyone, this is Shri Guru over here. Welcome back to my YouTube channel. In the previous video, we have started a dual nature of matter and radiation. In that, we have discussed the types of electron emission and properties of photons. In this video, we are going to continue a photoelectric effect. Whatever we have discussed in the electron emission, this is the continuation part of that. It is one of them, photoelectric effect. It is the phenomena of emission of electron from the surface of metals. When a radiation of suitable frequency fall on them, the emitted electrons are called photoelectrons and the current so produced is called photoelectric current. Hertz observations. The phenomena of photoelectric emission was discovered by Heinrich Hertz in 1887 when he was working with his electromagnetic wave experiment. Later, Halbach and Leonard detailed study the photoelectric effect during 1886 to 1902 experimental study of photoelectric effect. This is the experimental arrangement which consists of evacuated glass tube which is made up of quartz glass, which is having the window W, which is made up of quartz glass, which allows a particular frequency and a wavelength of light, and that is provided by the source S, which we have kept here. And there are two plates arranged here. The plate C is called a photosensitive plate or a emitter plate, and this plate A is known as an anode plate or a collector plate, and this is the commutator. By using this, we can change the potential of the plate A and C, positive or negative. And this voltmeter measures the potential difference between the plate C and A, and this micrometer measures the photoelectric current through the circuit. And this is the external battery which provides the potential difference to these plates. And this rheostat, by using this, we can increase or decrease the potential of the plate A with respect to the plate C. This is the simple arrangement of experimental study of photoelectric effect. Next, the experimental results of photoelectric effect. Before going to analyze the results of photoelectric effect, how we perform it. When a monochromatic radiation of suitable frequency obtained from the source S, after being filtered by a filter W, fall on the photosensitive plate C, the photoelectrons are emitted from C, which get accelerated towards plate A if it is kept at a positive potential. These electrons flow in the outer circuit, resulting in the photocurrent. Due to it, the micrometer shows the deflection. The readings of the micrometer measures the photoelectric current. This is how we measure, this is how we perform the experiment. Now we analyze the results of photoelectric effect. This experiment arrangement can be used to study the variation of photoelectric current with intensity of the incident radiation first. Second, photoelectric current with the potential difference between the plate C and A. Next, photoelectric current with the frequency of the incident radiation. Next, photoelectric current with the nature of the material of the plate C. Look at the first effect of intensity of the incident radiation with the photocurrent. Look at the first diagram one more time. Here we have kept this collector plate to a certain positive potential or a fixed positive potential, and we have choosing a particular suitable frequency of the light. As soon as the light from the source S entered through this window and finally fall on the photosensitive plate, the electrons are ejected from the plate C and accelerated towards the collector plate A, which is connected to a positive potential. As we go on increasing the intensity of the incident radiation, the photoelectrons ejecting from the photosensitive plate is also gradually increases, and therefore the photocurrent through the circuit also increases, and that can be measured by using the micrometer. If we plot the graph by choosing along the x-axis intensity of the light and along the y-axis photoelectric current, we will get a linear line which is originating from the origin. This shows that the number of photoelectrons emitted per second is directly proportional to the intensity of the incident radiation. It means that photoelectric current depends on the intensity of the incident radiation, not on the frequency, because we have kept the frequency constant. Second effect of potential of the plate A with respect to the plate C. One more time, observe the diagram. Here we have keeping the plate A for a particular accelerating positive potential with respect to the plate C. Illuminate plate C with a radiation of fixed frequency nu and intensity I1. Vary the positive potential of the plate A gradually and note the photoelectric current each time. It is found that photoelectric current increases gradually with increase in the positive potential of the plate A. For a certain positive potential of the plate A, the photoelectric current becomes maximum or a saturate. After this, if we increase a positive potential of the plate A, there will be no increase in the photoelectric current. This maximum value of photocurrent is known as a saturation current. The saturation current corresponds to the state when all the photoelectrons emitted from C reach the plate A. That can be observed through the graph here. Here we have chosen the fixed intensity, only we are changing the potential of the plate A. For a zero potential also there is a minimum photocurrent, but as we further increase the potential of the plate A with respect to the C, the current will come to the saturation or a same photocurrent. There will be no change in the photocurrent. Now one more time, go back to the diagram. Now we apply the negative potential on the plate A with respect to the C. We will notice that photoelectric current decreases. It is so because photoelectrons emitted from C are repelled and only energetic electrons are reaching the plate A. Increase the negative potential of the plate A. Gradually, we will note that the photoelectric current decreases rapidly and becomes zero at a certain value of negative potential V0 on the plate A. At this stage, even the fastest electron cannot reach the plate A, and that can be observed through the graph one more time. See the diagram here. As we go on, increase the negative potential of the plate A with respect to the C, at particular decrease in the potential of the plate A with respect to C, the photoelectric current becomes zero. Now, this minimum negative potential V0 given to the plate A with respect to the plate C, at which the photocurrent becomes zero, is called a stopping potential or a cutoff potential. If E be the charge of photoelectron, then K maximum is equals to EV0 is equals to half mv square. This is the kinetic energy of ejected electron from the emitter plate, where m is the mass of photoelectron and v is the maximum velocity of emitted electron. As we change the intensity of the incident radiation, but we keep the frequency constant for these two of radiations, but this I3 and I2 are greater the intensity, therefore the saturation current is get increased, but the stopping potential for this radiation is also same because the frequency of this radiation is the same. as we have chosen for the I1. Next, the third effect of frequency of the incident radiation. Take the radiation of intensity of frequency but the same intensity. From this we can conclude that first, all the photoelectrons emitted from the plate C are not having the same kinetic energy. Second, for the radiation of a given frequency and the material of the plate C, the value of the stopping potential is independent of intensity of the incident radiation. It means the maximum kinetic energy of emitted photoelectrons depends on the radiation's source and the nature of the material of the plate C, but it is independent of intensity of the incident radiation. Look at the third effect of frequency of incident radiation. Take the radiation of different frequencies but the same intensity. Study the variation of take the radiation of different frequencies but same intensity. Study the variation between the photoelectric current and potential of the plate A with respect to C. Variation can be shown here in this in the graph. The value of a stopping potential is different for the radiation of different frequencies. Here we have chosen a different frequencies V1, V2, V3. V1 is less than V2 is less than V3. Here, therefore, the stopping potential is different for the different frequencies. The value of the stopping potential is more than negative for the radiation of a higher frequency. This means as we increase the frequency of the incident radiation, the stopping potential is also gradually increases. The value of saturation current depends on the intensity of the incident radiation, but it is independent of frequency of the incident radiation. For all the different frequencies, the saturation current is the same. This shows that this saturation current is depends on the intensity of the incident radiation, not on the chosen frequencies. Next, the same by plotting the graph between the frequency of the incident radiation and a corresponding stopping potential for the different metals, we get a straight line as shown in the figure. Here we have chosen a different metals plate, metal A and metal B. For this there is a different cutoff frequencies. Along the x-axis we have chosen the frequency of the incident radiation, and along the y-axis we have chosen the stopping potential. For different metals they have the different cutoff frequencies. As we further extend these lines backward, these lines get intercept the stopping potential of the negative x-axis, which is denoted by phi by E. The work function for E is E into magnitude of the intercept of the potential axis. For a given photosensitive material, the stopping potential varies linearly with the frequency of the incident radiation. There exists a certain minimum cutoff frequency V0 for which the stopping potential is 0. The higher is the work function for a photosensitive material, the greater is the value of threshold frequency. The maximum kinetic energy of the photoelectrons varies linearly with the frequency of the incident radiation but independent of intensity. These are the observations from this graph. Finally, by observing all these variations with respect to different physical quantities, we give the laws of photoelectric emissions. The first law is the given metal and frequency of the incident radiation, the number of photoelectrons ejected per second is directly proportional to the intensity of the incident light. Second, for a given metal, there exists a certain minimum frequency of the incident radiation below which no emission of photoelectrons takes place. This frequency is called threshold frequency. Third, above the threshold frequency, the maximum kinetic energy of emitted photoelectron is independent of the intensity of the incident light but it depends only upon the frequency of the incident light. Fourth, the photoelectron emission is an instantaneous process. Within a 10 raised to minus 9 seconds it takes place. Thank you for watching my video. Don't forget to like and share and subscribe.